Okay, welcome back. We are going to continue our study of the spacetime algebra. And in particular, I want to say we're really going to continue our study of the geometric algebra. And we're using spacetime algebra as our favorite exemplar, first of all, because it's probably the most physically relevant, although the geometric algebra of regular 3 dimensions is also pretty straightforward and interesting. It's a lot easier. And from time to time, we'll probably use some examples in the Euclidean 3-dimensional space algebra, I guess we would call it. But we're following this paper, and this paper is all about the spacetime algebra. And so we have gotten through most of the spacetime product, and let us review where we're at and then push into multivectors today. So we definitely did the axioms of the spacetime algebra, which apply just to members of M13, right? These are the vectors, right? So all of this stuff just applies to the notion of vectors, which, of course, in spacetime algebra are 4 vectors. If you speak about geometric algebra in general, then these axioms apply just to the vectors, and sort of these are like the base space. And when we think of our 4-dimensional spacetime, we're thinking of the 4 basis vectors in this base space. And these axioms only apply to those 4. And then we immediately saw that this last axiom made us expand our algebra to include at least the real numbers, because the spacetime product of any vector with itself was the Minkowski contraction. And we realized that right here, this is where we force special relativity into our problem. By saying that the magnitude or the spacetime product of any vector with itself is equal to the Minkowski contraction of a vector with itself, that's right in there. That's the metric is literally built into the algebra right there in that statement. And if we were doing Euclidean algebra, if we were or using just the Euclidean 3D, then this wouldn't be present. It would be a different statement. It would be, let's see, it would be much simpler. It would be just this Pythagorean multiplication. I shouldn't say that. It's just the sum of the squares of the components of each of the 3 dimensions would be what the magnitude squared would be. And you wouldn't have to worry about epsilon alpha, because this would always be positive. You have a positive definite metric. But our algebra works fine with a pseudo-metric or a non-positive, an indefinite metric. So we understood that, and then we moved on, and then we actually started beginning some definitions. We said the spacetime product of any 2 vectors, it has a symmetric part and an anti-symmetric part, which is just an algebraic statement, right? The only thing we're not assuming is commutativity, of course. And we define the symmetric part to be B dot A, and we define the anti-symmetric part to be this thing A wedge B. Right? No, those are just symbols that attach themselves to the symmetric and anti-symmetric part. And then we demonstrated that this B dot A necessarily, because of this earlier axiom, must end up being the Minkowski contraction of A and B, which is why we chose the dot there, because it's like the dot product of these 2 vectors. And then down here, it wasn't quite as clear, right? We had a symbol to represent the anti-symmetric part, but we need something that is truly anti-symmetric and involves 2 vectors. And we basically went back to our experience with other branches of mathematics, namely the theory of the exterior calculus, and we said, hey, there's something out there that is a geometrically interpretable thing, and it satisfies this rule beautifully. And when we examined that, we decided to interpret this anti-symmetric part of the spacetime product as this circulating area that has no particular shape, but is defined as the vector A swept across the vector B, and that would define a little region in the plane. But if you take this too literally, you end up with this sort of parallelogram shape. But in principle, as the authors point out in this picture, the shape is arbitrary. In fact, the shape is not even arbitrary. It's just, there is no shape. It's just an area. And with that interpretation, now we have a geometric interpretation of the symmetric part, which is the magnitude of these two vectors. So in other words, if you believe in the geometric interpretation of the vector as a little pointy thing in space, in our case, four-dimensional Minkowski space, then the symmetric part gets interpreted as the Minkowski contraction. The antisymmetric part gets interpreted as an element of plane, oriented plane with a circulation. The circulation, the orientation of this thing, there's two parts of it, right? A and B have components. So in principle, you would understand that this is sort of sitting out in space and has a certain alignment, but it also has a circulation, right? So there's two kinds of orientation. Usually when we talk about the orientation, though, you're talking about the circulation direction. And that's the wedge product, right? That's the wedge product. So now we can break up the space-time product between two vectors, right? And that's really critical. The only thing we know is how to take the space-time product between two vectors. And then we added real numbers to our algebra, and now we need to add these plane pieces. Because remember, the space-time product of any two things in the algebra, this has to be part of the algebra. That's a real number. We've already kind of added that in there. But these bivectors, these plane pieces called bivectors, we had to add that in as well. So now our Clifford algebra, we've added the real numbers. We have our vectors, which in the paper we're going to call these basis vectors for M13, gamma 0 through gamma 3. And we understand them to be four vectors of special relativity. And we also are, but we'll mix that between E0, E1, E2, and E3. And I'll make the transition soon enough. And then we add our bivector space, right? And we call this the bivector space, and it is written as capital lambda sub 2 of M13, right? That's all of the bivectors where the vectors come from M13. This is sort of notation that comes from the exterior calculus. So that's this next vector space that we add. By the way, I might have mentioned in a previous lesson that each of these was a subalgebra of C13, and that's not correct. They are as a vector space. C13 is a vector space, as all algebras are, and these are definitely subspaces of that vector space. So this is a vector space, which is a subspace of the vector space C13, but is not a subalgebra because there's no product defined that stays closed inside this. Obviously, the space-time product between this vector space completely leaves the vector space. So if I said any of these are subalgebras, that's incorrect. I think a viewer called me out on that, and they're right. I knew that, but it's so tempting to say, oh, this is the algebra, the geometric algebra, and these are subalgebras. That's incorrect. These are vector spaces in their own right. The only algebra in sight is this complete Clifford algebra. Thank you to whoever pointed that out. And I've done a little bit of foreshadowing here. Just as we've added the bivectors, in this lesson we're going to understand that we add the trivectors and the quad vector. And there will be 4 trivectors and 1 quad vector. And those will complete the entire algebra of C13. And each of these are closed vector spaces in and of themselves. So this is a little foreshadowing, and that will complete all of these spaces. This quad vector we're going to learn is also called the pseudoscalar of the algebra. And that is very, very, very important. The idea that there's a pseudoscalar, because it's one-dimensional, right? So it's very similar to this. This is one-dimensional too. So this is the regular scalars, and this will be the pseudoscalars. These will end up being the regular vectors. These will end up being the pseudovectors. Remember how we talked about the distinction between vectors and pseudovectors is kind of slapstick and arbitrary. What's the right word? Slapstick and arbitrary, the correct word for that in science is ad hoc, right? The notion of vectors and pseudovectors in the previous formalism, it's an ad hoc addition to the formalism. But this is natural in the formalism. You don't have to track the distinction between two things that have geometrically the same idea, right? Two vectors, and say, oh, remember, this one, though, is a pseudovector, and this one is a regular vector. Now, you have a completely different geometric object, which will be an oriented volume, oriented three-dimensional volume, and this will be an oriented four-dimensional volume, and it is our pseudoscalar. So now you have two different types of scalars that are completely distinguished geometrically, and they behave exactly like the ad hoc versions of scalars and pseudoscalars in the previous formalism. So this is one of the reasons why people love this formalism so much. And let's see, and notice, of course, there are 6 dimensions to this bivector space, and any oriented plane area can be broken down as in these components. And the way that would look in component form is F alpha beta E alpha wedge E beta. Now there is an issue here. When you look at this, you're sort of double summing. But if F is anti-symmetric, that's okay. So F will end up having to be anti-symmetric because you're double summing over things that are not linearly independent, because, for example, E0 wedge E2 is equal to minus E2 wedge E0. So if you took this sum literally, you are double counting every basis vector. But if this is anti-symmetric, then you'll compensate for that negative sign. So that's why these components inherit anti-symmetry from the anti-symmetric nature of the wedge product. Okay, so that's a little bit of review to this point and a little bit of foreshadowing. So let's move on. So the vector product combines the non-associative dot and wedge products into a single associative product. So we haven't done these two paragraphs yet. Now, that paragraph to me, that statement is a little bit weird because the dot product between two vectors, A dot B, right? If I take two vectors, this dot product is a scalar. So I can't take another dot product, because you can't take a dot product with a scalar. And so you can't really even write down you can't really create an association. So it is truly non-associative in the sense that it's not logical to talk about associativity when you have an operator that only works in a binary way. So sure, I guess the dot product is non-associative. The problem really is with the wedge product, because it's also true that A wedge B, if you restrict it to just two vectors, right, then A wedge B isn't associative, but you can do A wedge B wedge C. That is a thing that exists, but that is in fact associative. A wedge B does in fact equal A wedge B wedge C, which is exactly why you never see parentheses around these things, because it's totally associative. So the wedge product is actually associative, but so I think what they're getting at is, if you look at this expression, they say, well, this guy is associative, which means A, B, C, you can split that up into this or into this, right? You can put those parentheses either places. But individually, these guys are not associative. But when you combine them in this way, you get something that's associative. And the authors found that interesting and pointed that out. The result of the product, the spacetime product, thus decomposes into the sum of a scalar and bivector parts, which should be understood as analogous to expressing a complex number as the sum of distinct real and imaginary parts. Okay, so this is the hand-waving argument of why you can add a scalar to a bivector, right? So because that's what's going on here, right? We are adding a scalar to a bivector. This is a scalar and that's a bivector. So this is a real number like 7, and this is 3E0 wedge E1 plus 2E2 wedge E3, right? That's a bivector right there. Right, so this part is bivector and is understood as some kind of oriented area in the plane. And this is just a straight up real number. And yet we're adding them together, right? Which We're adding apples and oranges. And we always learn you can't add apples and oranges. But they're saying, oh, no, I know you've learned that, but you've ignored it when you write a complex number. And if you write 7 plus 3i, you'd have no trouble with that because you understand this complex number is best understood as one thing, even though it's split into two parts, and you never combine it into one part. And for example, a e to the I theta, right? You can convert this form into this polar form, and it kind of looks like one thing, but understand that's not one thing. That's a, cosine theta plus I sine theta. This is two things. And the definition of this is still the sum of real and complex parts through the Taylor expansion, right? So what they're trying to say is, don't worry about adding these things together because you've already jumped into that well. So just keep jumping, right? We don't have to study this notion of this addition because you've already bought into it, so let's just move on, which is completely appropriate for a review paper that's saying, look, we're not here to answer every conceivable question you could ever ask in the world. We're just here to get you moving on this subject, right? So don't worry about this addition. On the other hand, I'm very worried about the addition. So I am going to do a section talking about that addition. But this is a fine way to proceed. Just say, hey, look, you can add these things together. Just sort of treat it the same way you do a regular complex number. And then they go on to say, just as with the study of complex numbers, it will be advantageous to consider these distinct parts as composing a unified whole rather than separating them prematurely. Yeah, so imagine you had a complex number, 7 plus 3i, but all of your math demanded you work on just this part or just that part. You had a universe of math for this and a universe of math for that. You wouldn't be, you would be reproducing, you wouldn't even be reproducing it. You would lose the ability to do complex analysis. So we'll explore this similarity more thoroughly in section 3.5. So what they're anticipating there, and it's pretty an important thing that people who love geometric algebra love to talk about is there is no imaginary number, right? This entire algebra is real. All the scalars are real. Let me make that clear. So all of these vector spaces, right? The scalars that you can multiply, you can add vectors together, and you can multiply any vector in a vector space by its appropriate scalar. And what's important is that in all cases, the bin of scalars that they're looking at are real numbers, right? They're just real numbers. You never see a complex vector space, and this one there's an extra bin of real numbers right there, right? You never see complex numbers show up anywhere in this study. And what we're going to do is we're going to show that there are pieces of this algebra which act as the imaginary number. And the pseudoscalar is probably the most important of all of them because this thing squared is real important. But there are other pseudoscalars buried in here. So quaternions and complex numbers are actually subalgebras. They're literal, in that case, they literally are subalgebras of C13. And eventually we'll get to seeing why that is. And so to finish off our last paragraph here, a significant benefit of combining both the dot and wedge products into a single associative product in this fashion is that an inverse may be defined. Now first, about this inverse, notice it's an inverse for just the vectors, right? So the only things that they're talking about here are the members of M13. Those guys get an inverse, and not even all of them get an inverse, because this is a scalar down here, this a squared. So if that's 0, and in Minkowski space, if A is literally a light-like vector, which they actually say here, then this isn't going to make any sense. But other than that, every vector will have an inverse. And it's pretty easy to see, right? If the space-time product of A with itself is the number A squared, right, with this epsilon here, then clearly if you define a new vector A inverse in this way, this A squared will be in the denominator and it'll all cancel and you'll get a 1, right? This number A squared, right, will be in the denominator. This all cancel and you'll get a 1. So clearly every vector has an inverse in the space-time product. It doesn't apply to the bivectors or the trivectors or other combinations yet. This definition, as they described it, shows that it just applies to the vectors of M13. And in fact, overall, it is not true. Well, we already showed it's not true, but it's not true for a general element of the Clifford algebra. It has an inverse. That's not correct, or a unique inverse at least. Importantly, neither the dot product nor the wet product alone may be inverted. Only their combination as the sum retains enough information to define an inverse. And what they're saying there is if I have A dot B, I end up with a real number, eta A B, right? And say that number was 7. From 7, I can never really go back and figure out what A and B were. And that's also true of A wedge B, right? And we show that A wedge B plus epsilon A, right? If I have A wedge B and I add to B some value of some other vector that's in the direction of A, co-aligned with A, which I'm writing as epsilon A, I break that up by linearity and I get A wedge B plus epsilon A wedge A. But epsilon A wedge A, of course, is 0 because any vector wedged with itself is 0. So if I'm sitting on A wedge A, if I'm sitting on some area, some circulated oriented area, I can't get back uniquely to the two vectors that produced it. There are many vectors that could have produced that area. So it's not invertible either. And that's what they're getting at there. Okay, so with all of that, we're now ready to talk about multivectors. So I thought a bit about how to approach this, and what I'm typically doing is I'm reading the text and I'm kind of expounding on the text and filling in what I think are, since we have an infinite amount of time in these lessons, I'm filling in all of the gaps that I find in there. The backstory, right? If this was some kind of fictional world where there's a lot of backstory that's unexpressed, I'm kind of filling in the backstory. But in this case, with multivectors, what I'm going to do is I'm actually going to start with some backstory, and then we're going to attack the text. And the text will actually look very simple because these authors do quite a bit to simplify the space-time algebra. And if you just read through their paper and you attacked it as they present it, you would end up with this beautiful picture, and I can't wait to get to it. But it's a very simplified version of how things work in the space-time algebra. And it's efficient and it's smooth. I kind of want to demonstrate it the hard way a little bit so you can appreciate the simplicity that they give you. I'm not going to dive too deeply into it, but we'll start their section a little bit after we do some of our own work, all right? So let's pause the paper and begin a study of multivectors. So first, our global picture, right? Although with the caveat that we have yet to kind of dive into these things, although we're probably not going to dive in too deep, I'm just going to lay it out that this is the space-time algebra, the Clifford 1-3 algebra, and it's made up of the graded sum of these 4 vector spaces. We still need to talk about how this sum is done, but for the moment, you're going to fake it till you make it using the prescription that they offered earlier that's, it's just like complex numbers. So, this is a real number. This is sort of like a complex number. This is sort of like another complex thing, like quaternions have 3 different, complex square roots of -1. They're all different. So we have 4, big deal. So we're going to push this under the rug for a minute, and we're going to understand that we can now create a vector in this space, a vector in this space, a vector here, a vector here, a vector here, and somehow we can add them together. And anything that we do by creating vectors in any combination of these spaces and adding them together, those things are elements of the vector space Clifford 1-3, and they are part of the Clifford algebra. They're closed under space-time multiplication, which makes them part of the Clifford algebra. And that universe of things are called multivectors. So a multivector would be, a real plus some bivector A wedge B plus some trivector C wedge D wedge E plus some quad vector F wedge G wedge, wedge H wedge J, right? If I add these four things together, I get some sort of multivector. Any sum like this is a multivector. Now, those multivectors don't have to have each part, right? I could have a multivector with just a trivector and a real number. I could have a multivector with just a bivector and a quad vector. I could have a multivector which is just a bivector. Now, if I had a multivector that was just a bivector, that's actually given the name a blade. And in fact, this would be called a two-blade. Now, I know we've already said this, we're going to call it a bivector, and a two-blade is a bivector. The reason we want to go with blades is we don't want to say, bivector, trivector, quad vector, quintavector if they were a larger dimensional space. You can't have more than a quad vector, of course, because if you wedge another vector to it, you're going to get 0. But this would be a two-blade, and this would be a three-blade, and this is a four-blade, right? Now, and then this is a zero-blade, right? And so every multivector is some combination of 0 blades, 2 blades, 3 blades, and 4 blades. Now, importantly, there is notation for this. And I'm going to fast forward into this notation a bit. And if we have a multivector M, M has a 0 blade part that we describe by these angle brackets around M. It has a 1 blade part, it has a 2 blade part, and it has a 3 blade part. So this is the notation that we use. 1 blade part, 0 blade, 1 blade, 2 blade. Oh, I forgot the 1 blade up here, didn't I? Look at that. So hold on, there's this. I move that over. And I add a 1 blade part, which would be say the vector W, right? So there's a 1 blade, a 2 blade, a 3 blade, and a 4 blade. So now I need to add my 4 blade. And there's plus a 4 blade part to the vector M. So the vector M has these 4 parts to it. Now some of them may be 0 and some of them not. And it may only have 1, in which case M is a pure blade, right? If this was 0, this was 0, this was 0, and this was 0, then M would be a 1 blade or a vector. Yeah, make it clear. This is the 1 blade and that is the 0 blade. The real number is the 0 blade. Okay, so that is sort of the notation of what a multivector is. And we can take the space-time product of any multivector with another multivector. So if I had another multivector, which I'll call, say, capital N, I can create the space-time product of M and N, right? Just by putting them next to each other. And by linearity, this is very easy to take apart. So the idea is if we have M as a multivector, and it's some sum of these 4 different types of blades, and H is a multivector, that's some sum of 4 different types of blades, MH is the space-time product of this multiplied by this, which is, it's a pretty big expansion, but the first term is going to be the 0 blade of M times the 0 blade of H. And the last term is going to be the 4 blade of M times the 4 blade of H. And you're going to have every combination of blades buried inside there that are going to be part of this sum. So the point of this slide is to show that we can do the space-time product of two arbitrary multivectors as described here. But we have to know how to do the space-time product of every one of the blades with every one of the other blades. So our mission now is sort of to understand the space-time product of vectors with bivectors, of vectors with trivectors, of vectors with quad vectors, or the pseudoscalar, bivectors with bivectors. We already know vectors with vectors, so we've solved that one. But now we need to know vectors and bivectors, and we need to know bivectors and trivectors. and bivectors and quadvectors, and we need to know trivectors and quadvectors and all of that stuff. So we need to understand all of these different blade products in order to fully understand how this algebra works. And here's a little secret. Very few studies of geometric algebra really do that in full generality. And even our work here, we're not going to do it in full generality, but we are going to pursue it substantially and then focus on just what we need to know for the spacetime algebra. So we're going to take a bit of a digression into vectors times bivectors, and then we're going to describe bivectors times bivectors and bivectors times trivectors. And we're going to describe all of these things and then move into the way the paper wants you to understand the structure of geometric algebra. So we'll just attack one very thoroughly, and then we'll wave our hands and assume some of the others. But the one we're going to attack is the vector times a bivector. The vector times a bivector. So A is the bivector, so it's an element of the bivector subspace of our Clifford algebra. And we're going to say that that bivector is U wedge V. So you can already see that we're going to use a proper formalism here. We're not breaking this down into components. We're going to use a proper formalism. And W, U, and V are all part of the subspace of the Clifford algebra that is M13, right? It's an element of M13. Lambda 1 of M13, by the way, is in fact M13. Lambda 0 is just real numbers. So it's a little excessive, but this is to show that we're considering M13 sort of as part of the Clifford algebra. And then we're going to form the spacetime product of the vector W with the bivector A. And we're going to write that as W spacetime product of U wedge V. So we're going to proceed and analyze this and see if we can understand what the spacetime product of W and A looks like. Well, we know what U wedge V is because U and V are vectors from M13, so we know that this is the anti-symmetric part of the spacetime product of U and V, which is exactly what this term here is, right? UV minus VU times a half. So that is by definition a true statement. And then we just use linearity and we bring in the W, right? So we get WUV minus WVU. And this is a triple spacetime product of vectors. No problem there. You can always do that. Because remember, spacetime product of U and V is in the Clifford algebra. So that's just a member of the Clifford algebra, and so is W. And we know, actually, UV is going to be U dot V plus U wedge V. But if you made that substitution, you would just go back. But we're blowing this up into this triple vector product. And then to show kind of how annoying these proper proofs can be, or these proper analyses can be, I don't know if I would call this a proof as much as an analysis, is I take this WUV and minus WVU and I make all these very clever observations about how it's going to end up. Basically, when I did this work, I actually started from the end and went backwards. But as long as you see how each step is logical, you can appreciate the final result, right? So we move the WUV, WV goes here, and we're going to add to it UWV, and then subtract UWV. So we're adding 0. And then we have the minus VWU part from our previous line, and we subtract VWU. No, we bring down WVU, and we subtract VWU, and we add VWU. So that's adding 0. So we've taken this and added 0 in this unique form. And then, of course, we're going to cleverly regroup, and we get WUV plus UWV for this first term, and then WVU plus VWU, right, with the minus sign coming out in front. And then the things that are left over is this minus UWV and this plus VWU, which is correct if you add these minus signs. So I've got these little arrows showing us how we're going to regroup things. So what's nice about this first piece that we've regrouped is that we have V at the back. So I can pull a V out. And then the second one, I have U at the back, so I can pull a U out. And this third one, I don't have v or u at the back, or u or v at the front, or anything, so I leave it alone. And what's important now is I look at this, I say, well, that's the symmetric part of the space-time product of WU. And this is the symmetric part of the space-time product of WV, right? So I know what those things are. Those are the Minkowski contraction of W and U, and this is the Minkowski contraction of W and V. So I replace it with these little dot products, which indicates that. Remember, this equals Minkowski WU, and this equals Minkowski contraction of W and V, right? So with that, then I'm left with this piece over here. So I'm going to rewrite this, and I'm going to rewrite this with these Minkowski contractions. So now I have this thing to work on. This is actually pretty clean. That's a real number times a vector. That's a real number times a vector. So this part here is just a vector. This part here is some kind of triple space-time product. It almost seems like we've made the problem worse, right? But I bring down these two, the vector part into this line, and I'm going to cleverly work on this part by the same process. I'm adding and subtracting stuff. And in this case, what I'm going to do is I'm going to add, I took this minus sign and I turned it to a plus sign. So I brought the minus signs inside these brackets. And the way it flows is that one dropped down to here and this dropped down to there, right? And I'm adding a UWV, which will cancel that. And I'm subtracting a VWU, which will cancel that. So I've canceled these parts to 0. So in order to do that, I've had to somewhere I have to compensate for those two, right? But I'm also going to add a UVW, and I'm going to subtract a VUW. Now notice these two that I've added and subtracted, they don't compensate for the two that I just added and subtracted to, or that I added to cancel. So I'm trying to cancel these two terms. So I add this term and I subtract this term. So that cancels it. The two these two additional terms do not compensate for that, right? UVW is not UWV, and VUW is not VWU. But I'm adding those two in as well. And what I notice, and I'm doing that, of course, because I kind of know how this has got to end, right? It's very, very clever, but very hard to see, but it's very clever, and it's a bunch of algebra. So obviously, somehow I have to compensate for all of these four things. But what I notice is that UWV and UVW can be combined into this term, which is U times the symmetric part of the spacetime product of W and V. And these two can be combined into this term, which is a vector V times the symmetric part of the spacetime product of W and U. And so this is actually what I've added to these two terms to make the changes that I think are relevant, canceling this and leaving behind these two terms. So obviously, if I'm going to add this to this stuff inside the brackets, I need to understand these two is the same as this 1/2. These divisions by 2 come from here. So there's no division by 4 anywhere. But anyway, the point is I have to subtract it somewhere else. So I'm going to subtract it right here. What's convenient is this is a vector and this is a vector, right? These two things are vectors. So I just, I now subtract this part and add this part. And now this, which is in green here, is just U dot WV minus U times V dot W, a real number times two more vectors, just like these two guys. So now, and it turns out it's exactly the same as these two guys, because W dot U times V is U dot W times V, because U and W, this dot product, is commutes. And W dot VU is U V dot W, because this commutes and the real number commutes. So this can be combined with this, and this term can be combined with this term. So the vector v part can be added together and the vector u part can be added together. And you just get 2 w dot uv minus 2 w dot vu, which is nice. And then what's left behind is this thing right here. That is what's ultimately left of this mess, right? Is this just these two terms, this term here and this term here. And when you combine them, what you see is that you can pull out the w from the back and you get the antisymmetric part of the spacetime product of u and v times the vector w. But that antisymmetric part is by definition u wedge v w. So this thing here ends up being u wedge v w. So you can write w times u wedge v is this vector piece plus u wedge v w. And now this, there's no reason to think this commutes at all, right? This stuff does because we know that that's just a scalar real number. But this wedge product, the spacetime product of a wedge product and w, we can't, it doesn't commute. But if I take this and I move it over to the other side, right? If I take what's left over here and I move it to that side, I end up with w u wedge v minus u wedge v w equals this vector. And if I clear the 2, I get w u wedge v minus u wedge v w over 2 equals this vector. Well, if you look at this, this is the anti-symmetric part of the spacetime product of w with the bivector A, right? Here's the bivector A, u wedge v, and it's w times u wedge v minus u wedge v times w over 2. That's the anti-symmetric part of this product. So we define that. We are going to define the anti-symmetric part as w dot A. Now notice we used to define the anti-symmetric part as, or we used to define w dot A as the symmetric part of something, but not this time. This time we are going to define it as the anti-symmetric part. So when we're talking about a vector spacetime product with a bivector, the anti-symmetric part is going to be is going to be associated with the dot product. Now notice we can't say that this dot product equals eta omega A, right? Because that's not how Minkowski metric works. The Minkowski metric only works with vectors. It doesn't work with bivectors. That doesn't even make sense. There's no such thing there. So we're actually creating this sort of new notion of a dot product, and we're associating it with the anti-symmetric part of this product. And it's a vector. It's not a scalar. So this dot product doesn't even give you a scalar. It gives you a vector. So this is a mathematical notational convenience we're introducing here. And I'll explain why in a moment. Well, I'll explain why right now. Let's look at our notion. We have a vector times a bivector. And we are now saying that the anti-symmetric part we're going to call w dot A. The symmetric part is going to be w wedge A. And we're going to do this sort of by definition, right? It has an anti-symmetric part. It has a symmetric part. So we can just sort of rename these things. Now we just discovered this is a grade 1 object and this is a grade 2 object. Bivectors have grade 2. They're 2 blades. If I didn't say that before, 2 blades have grade 2, 1 blades have grade 1, 0 blades have grade 0. That is, this number down here represents the grade of that part. So the grade 2 part of M is whatever this number, whatever this 2 blade is. The grade 4 part of H is whatever this object is. So over here we have a grade 1 object and a grade 2 object, and we know that it devolves into a grade 1 object. The symmetric part is a grade 1 object. So that just leaves this anti-symmetric part, which we write down as w wedge u wedge v, because A is u wedge v. So the anti-symmetric, or this piece is now a 3 blade. So this object breaks into a 1 blade and a 3 blade. Now there were kind of 3 grades on the left side, and it drops to a 1 grade and a 3 grade on the right side. So what we're saying now is that the dot product is the piece of this spacetime product that lowers the grade by 1. And the wedge product is this piece of the spacetime product that raises the grade by 1. And this can be done whenever you have a vector as part of the spacetime product. What the vector will do is it'll take the grade of the whatever it's multiplying by, in this case a grade 2 object, but it could also work with a grade 1 object, a grade 2 object, 3 or 4. But it will give you two pieces, one which is one grade lower than what it's multiplying, what the vector is being, what the other factor than the vector. So the vector factor is grade 1, but this other factor is grade 2. This first piece is one grade lower than the grade 2 object. The second piece is one grade higher. If this was a trivector, then the grade 1 object would be a bivector, and the grade 4 the dot piece, the dot product piece would be a grade 2 object, a bivector, and the wedge piece would be a grade 4 object, a quad vector. So, but in this particular case, this dot product ends up getting associated with the anti-symmetric part, and this grade 3 part gets associated with the symmetric piece of the product. And this always confused me because you're looking at the symmetric, the symmetric part of this product is something which is the ultimate anti-symmetric object, right? It's the ultimate. How can this deeply anti-symmetric object be associated with the symmetric part of anything? But of course, the answer is actually pretty obvious when it clicked in my head, which is if I switched and wrote A W, I would have to switch A with W, and the U would move over 1, bringing a minus sign, and then the V would move over 1, bringing another minus sign, and those two would cancel, and you would end up with U wedge V wedge W, right? So the symmetry of this deeply anti-symmetric object actually is exactly what you need to define this symmetric part of WA, because the two minus signs cancel when you make this movement. In other words, you start with WUV and you switch the W and the U and you get minus UW, and then you switch the V and the W and you get UVW. So you've switched A is right over here, and now A is on the the right side, and now A is on the left side. And obviously you switched A and W and the sign didn't change. So that is symmetric. So that's the symmetric part of the product, and we define it to be this completely anti-symmetric object, which is kind of interesting. And then we learned that we just figured out that the grade 1 part is equal to this vector here, So that is the mechanics of proving how you do multiplication of a vector and a bivector, right? So we could spend a little bit of time interpreting what this object is. This object's easy to interpret, right? It's a fully anti-symmetric thing. We consider this a little unit of 3 volumes. So it's a parallelepiped, 3-dimensional parallelepiped living in 4-dimensional space. And that's how we choose to interpret this thing. Now that interpretation is, it's a bit of a risk because all it is an algebraic object, but we've learned that there's this geometric thing that is very, very aligned with this algebraic construction. And so we just go ahead and we make that interpretation, just like we did for a bivector. So this guy is easy to interpret. This guy, not so much, right? It's the projection of W on part of A in the direction of V, and the projection of W on part of V, on part of A, V, in the direction of U, and there's that minus sign between them. So how do we interpret this? Let's talk about that for a moment. So let's do the setup here, right? Here's the plane element E1 wedge E3. This is the bivector. This object here is the bivector. I've even got to have its circulation. It's a unit bivector. It's a basis bivector, E1, E2, E1, E2, not E3, E1, E2. And we want to take the space-time product of E1, E2 with this vector V. So we're looking for V times E1 wedge E2, right? That's equivalent to VA in our previous analysis. So this is geometric objects. So you want to think, well, what could this be, right? Well, you got a vector and a plane. So what are the interesting things that can happen to a vector and a plane? Well, the vector could be in the plane or it could be out of the plane. And the way I've depicted it here, it's out of the plane. And you know it's out of the plane because I have a CE3 component. But this part is actually in the plane. So there is that question of its projection, right? So we know that so we know our formula is V dot E1 E2 minus V dot E3 E1. So what is this first term? It's the projection of V on E1, right? Which I guess we could draw as the projection of V on E1 would be something like that, right? And that distance should presumably be A. But that's just a number, right? That's the number A, but it's in the direction of E2, right? It's the vector now in the direction of E2. So I take A and I push it in the E2 direction. And then, but it's minus V dot E3 E1. Well, V dot E, not E3, E2. Why do I have E3 there? It should be E2, right? And V dot E2, well, it's some other number, but it's whatever number it is, it's some number, it's some projection on this axis here, right? But we projected actually minus on E1. So we project it onto E1 and then we get this minus sign. So we switch the sign. So we end up with a amount B over this way. And we add those things together and we get something that's in the plane, right? You'll notice that this result is in the plane. So this space-time product is, if nothing else, it's projected this vector into the plane. But notice that minus sign really throws us for a loop, right? Because if it was simply a projection in the plane, it would have just dropped into the plane and we would have gotten some vector like that. But we didn't. We got a vector like that, but then rotated by 90 degrees. So this space-time product captures several things. It captures the projection of the vector into the plane that is identified by the bivector, but it also captures the orientation, the rotation, the circulation of the bivector by rotating it. So all the essence of the bivector is captured and preserved in this space-time product. You lose this component, this orthogonal component in this case, but you still capture the circulation. Now in principle, right, we're in four-dimensional space, right? So I probably, we could have had a DE0 here, right? But that would have been lost also because you'll notice that, this equation doesn't change at all, right? It's just the projection into the bivector parts. So it doesn't matter how many other dimensions you have. You could have E4, E5, E6, forever and ever. They'd all be gone. You're still just projecting into the plane element. So that's a way of interpreting this space-time product through this geometry. And in fact, when you study geometric algebra in simply 3 dimensions, this is a big deal. It's introduced very early, but it's really no different. It's the same in all dimensions. You'll notice that the metric doesn't appear here. So the fact that this is Minkowski doesn't seem to matter much for this interpretation. So that's an interpretation of this space-time product. It's a projection of the vector into the plane and then rotated 90 degrees in the direction of the circulation of the plane. That's the resulting vector that you get. Really sweet. Oh, wait though. I should be a little bit more careful, right? This is literally the grade 1 part of that space-time product, right? The full space-time product, if I had written it down correctly, I'm glad I caught this, right? Would have been this plus V wedge A, right? V wedge A, which would be V wedge, the way I've written it here, E1 wedge E2, something like that. If A is E1, E2, which it is, right? A is E1, E2. So this would be V wedge. So there's also that part, right? So the space-time product part has the grade 1 part and the grade 3 part, right? So I'm talking about how to interpret just the grade 1 part. So this whole thing is asking the question, how do we understand the grade 1 part of this space-time product? We already know how to understand the grade 3 part. This is just going to be the, well, while we're here, we might as well draw it out, right? This is just going to be the full parallelepiped that you get between all of these vectors, right? So that's what this piece is. So what I was missing in if my previous story would have been completely correct if I had a dot there, but now I'm blowing it up to include the full space-time product, which includes this wedge product part. Okay, so we're going to leave it there for now. Now all we've done though is, just to be clear, all we now know how to do is we can multiply vectors with each other, we can multiply vectors and scalars with each other, we can multiply bivectors and scalars, and now we can multiply vectors and bivectors. There's still a few other things to do, but we're not going to go into these kind of demonstrations quite as deeply. We're just going to talk about them in generality, and we'll do that in our next lesson. So I'll see you next time.